Welcome students in the lecture series of computer system architecture. This subject is one of the subject for semester 1 in BCA and for BCA and IT students. Today we will start number system, but before going to the topic we will discuss something. At first I will discuss why it is needed to learn computer system architecture. Basically, it will give you the clear view of the computer system, how it's work. Basically, it is needed how computer system works so that you can utilize it in a better way. Next, the various software requires the computer architectures, the basic knowledge of computer architecture. For example, operating system. Many the developers write their own operating system, but operating system design and implementation require the basic computer system architectures, the knowledge of basic computer system architecture. Another thing is this course is basically the hardware related course. That means it give you idea, the knowledge of how logic circuit works, how microprocessor works, that is CPU, how CPU works, random access memory works, microcontroller works. This is, and at the end of the study of this course, you will find it is easy to design a logic circuit, microprocessors, microcontroller, etc. Objective of the course is to understand the data representations, how data is represented internally. Next is digital logic circuit design. Actually, there is various circuits inside the computers. So how logic circuit is designed? There is various techniques to design logic circuits. How logic circuits is minimized. This is minimum number of circuits to get the same amount of work. We will study in this subject. Basic CPU and memory design. This is another objective, and another last objective is to understand the assembly language program. Assembly language program is one of the programming language that is the second generation language, was developed in around 1950s. Assembly language program is still used to write some codes for compiler, operating system, etc. We'll study it in the last few lectures. Assembly language program is also used to optimize the code which is written in C or C++. This is the syllabus. First syllabus introductions, unit 1 introductions, logic gates, Boolean algebra, combinational circuits, circuit simplifications, flip-flop, sequential circuits, decoders, multiplexer, registers, counters, and memory units. These are the basic elements of a computer's CPU, memory. These are the basic units. Next is number system. It is how data is represented internally. There is various kind of numbers. There's binary numbers, hexadecimal numbers. How complements is created. Complement of a number is generated. Fixed and floating point number representation. What is fixed and floating point representation? Character representation, addition, subtractions, magnitude comparisons, multiplication and division algorithm. For integers only. Next, basic computer organization and design. This is related to CPU, and the topic discusses the designs issues of computer organizations. For example, registers, bus system, instruction set, etc. There is central processing unit, how central processing unit is work, and in this unit we will discuss assembly language programming. Next is memory organizations. There are various type of memories, how it is organized. Input output organizations, that is, there's various type of input output devices and how they interact with the computer system with using interfaces, that is means IO modules. We will discuss in this unit. The books, there is one of the books is Computer Fundamental by Floyd and Jain. This book is basically for logic design and number system. It gives you the basic strong background to design the circuits. Next is Computer System Architecture by Maurice Meno. This is basically for CPU design, microprocessors and memory organizations. So both the books are important. There is some reference books, for example, William Stallings, Computer Organization Architecture, Maurice Meno, Digital Design, B. Ram, Computer Organizations. Another book is A.J. Doss, Assembly Language and Computer Architecture using C++ and Java codes. It is basically for assembly language programming. In this lecture, I will discuss a number system. From the day of civilizations, there is various methods to count things, different things. Initially, there is only one symbol, that is 1, and through this only one symbols, the human beings try to count various objects. That is, if we have to count 3, then it places 3 ones. If it count 4, then it places 4 ones, and so on. Then there is another symbol, zeros. 0 and 1 make it a binary symbols. Then it comes ternary symbols in this way. Now we are at present age in decimal systems. There is another number system, hexadecimal number system. Generally, human beings use decimal number system, which consists of 10 symbols, and computer uses binary symbols, that is, which have 2 symbols, that is 0 and 1s. Types of numbers. Natural numbers. Natural number means the number 0 and any number obtained by repeatedly adding a count 1 to 0. That means if you have 0, then you add 1, it becomes 1. Then if you again add 1, it becomes 2, then 3, then 4, and so on. Negative number means a value less than 0. Integers are the negative number, positive numbers, and 0. That means all the natural numbers, the negative of natural numbers, and 0. So an integer, a number, is a system for counting things in a simple systematic way. You can count negative and positive both. If you place it a number line, then integer represent the various points in the number lines. Another is exponent, representations of number. Exponent means power. Just as 2 to the power 1 is equal to 2, 2 to the power 2 is equal to 4. Here 2 to the power 2, 2 is the exponent. Here 2 to the power 3 is equal to 8. That means 3 is the exponent, and so on. 2 to the power 0 is 1. 1 by x square. That means if we inverse any numbers, Here 1 by x square, that means x to the power minus 2. If we write 1 by x cube, that means x to the power minus 3, and so on. In this way we can represent the number in the exponent method. Decimal number system means there is 10 symbols. For example, 375, it is represented as 3 into 100, 7 into 10, 5 into 1. You have read in standard 1 or 2 classes. Here the base is 10, so positive positions weight is 10 square, 10 to the power 1, 10 to the power 0. The 5 is known as least significant digit, and 3 is the most significant digit. The position weights increases from right to left, and it represented in exponent view as 5 into 10 to the power 0, 7 into 10 to the power 1, and 3 into 10 to the power 2, that means 375. A decimal number is a sequence of digit, that is a single unit, smallest unit of a decimal number is known as digit, and its base is 10. Each digit contributes to a value to the number. The value contributed by a digit equals the product of the digit times the weight of the positions of the digit in the number. The weight of the rightmost least significant digit is 10 to the power 0, that is 1, and the weight of any position is 10 to the power x, where x is the number of positions right of the least significant digit. Here the positions weight 10 to the power 0, 10 to the power 1, and so on. Now bits. What is bits? Here in the last few slides we discussed about decimal number system, but decimal number system consists of 10 different symbols. When we come to computers, all about binary arithmetics, that means it only consider 2 symbols, that is 0 and 1, that is binary numbers. Binary numbers have a number of bits. That means a single unit of a binary number is called a bit. A single binary digit is known as bit. It may be 1 or a 0. 1 stands for on and 0 stands for off. Here we use on and off positions since it is totally related to digital circuits. 1, if we represent 1, then it does not mean 1 volt, but it is a 5 volt, and off positions means 0.3 volt. When we read about the circuits, digital circuits, we will discuss on this matter. There is 2 possibilities, on and off. On is 1 and off is 0. Combination of bits stores the values. Internally all the data is represented as binary number systems, and in memory or in CPU that works only using the binary number system, that is bits, not on the decimal number system. In decimal number system there is various digit, and in binary number systems we call it bits. Data representations. Internally computers data is represented in any coded form. For example, if you see the keyboard has 104 keys. There is 26 uppercase alphabet, 26 lowercase alphabet. There is 10 numeric digits. There is special characters, etc. But all these letters and special characters have an internal code. We will see later on. When we press any key from the keyboards, it encodes the value in a binary format. That is known as a code. And this code is a binary system, binary number system. Values being represented may be characters, numbers, images, audio signals and video signals. We use computers for various reasons, to read characters, number, images, to visualize images, to listen audio signals, video signals. All this we senses in a different format, but computer stores in the form of ones and zeros. Although a different schemes used to encode each type of data, in the end of the code it is always a strings of zeros and ones. Since if you see the now characters or numbers or images, all are different things, but internally all this data is represented as zeros and ones. Now, how you convert decimal to binary system? Binary system means there is only two symbols, that is 0 and 1, and its base is 2. For example, let us take a binary number, that is 1011. In the decimal number system, we assign 10 to the power 0, 10 to the power 1 and so on. In decimal number system, all the position words are a multiple of tens, but in this case the base is 2, so in binary number system the position will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4 and so on. Now this one is the least significant bit, its position value is 2 to the power 0. Now next one is 2 to the power 1, next 0 is 2 to the power 2, next one is 2 to the power 3. In this way we assign the position words to the binary digit. How is the positive integer represented in binary? For example, 110, it is written as 1 into 2 to the power 2, 1 into 2 to the power 2, 1, 0 into 2 to the power 0. In this way, finally it comes as 0 plus 2 plus 4, that is 6. That is 0 into 2 to the power 0. The number digits as multiplied by the position weights. That is 0 plus into 2 to the power 0. This is 0. Then 1 into 2 to the power 1. This 1 is to 2 to the power 1 is equal to 2. 1 into 2 to the power 2. That is 4. Now all this added and it becomes 6. Now binary to decimal conversion means add all the values. A simplified method is add all the values whose positional weight where a one digit occurs. When you have a one digit, then add the position weight. If it is 0, there is nothing is to be added. Now let's take an example to clear the principle. Now here 1 0 1 0 0 1 1 0 0 1 0 1. This is a binary number. Now this is a position, so here is 1, so 1 into 2 to the power 0. Next is 0. Now it is deleted, that it does not consider this value. Only where the position value is 1, we will consider that positions. So 1 into 2 to the power 0, 1 into 2 to the power 2, 1 into 2 to the power 5. That means 1 plus 4 plus 32. That means 2 to the power 0 plus 2 to the power 2 plus 2 to the power 5. Ultimately, you get 37 decimal in decimal system. Similarly, another example, a positional, if there is a positional value is 1, then you add the positional powers of 2, that is 2 to the power 0, and when the value is 0, it is not added. Now decimal to binary conversion. First is division method. In division method, there is a step-by-step process that is known as algorithm. Start with your number, call it n in base 10, then divide n by 2 and record the remainder. If quotient is 0, then stop, else make the quotient your new n and go back to step 2. This process is repeated 2 and 3 and is repeated until the quotient becomes 0. Now remainders are recorded and they are written in reverse order. In other words, divide the decimal number by 2 until you reach the 0 and then collect remainders in reverse. Let us take an example. 22 is a decimal number. It is divided with 2. The quotient is 11 and remainder is 0. Again 11 is divided with 2. The quotient is 5 and remainder is 1. Again 5 is divided with 2. The quotient is 2 and remainder is 1. Now 2 is again divided with 1. 2 is again divided with 2. The remainder is 0 and quotient is 1. And now 1 is divided with 2. Now quotient is 0 and remainder is 1. Now all the remainders are recorded in reverse order. That is, at first 1, then 0, 1, 1, 0. 1, 0, 1, 1, 0. Now this is a binary number. Another example, in the similar manner, 56 is divided with 2, that is 28, it becomes remainder is 0. 14 is divided 2, it is 0. Then 7, then 3, and remainder is 1. Again 3 is divided with 2, the quotient is 1 and remainder is 1. Now when 1 is divided with 2, the quotient becomes 0. Quotient becomes 0 and remainder is 1. Now this is written in reverse order. This binary number will be 1, 1, 0, 0, 0. Another method is known as subtraction method. In subtraction method, subtract out the largest power of 2 possible without going below 0, repeating until you reach 0. That means then again there is a step. Place a 1 in each position where you could subtract the value. Place a 0 in each position that you could not subtract out the value without going below 0. Let us take an example. Let us take 21. How this process works. Now 21, 16 is subtracted from 21. Since 21's nearest value is 16, 16 is subtracted from 21, and the as we use 16 here, so place a 1 here. Now next the value is 5. 5 is subtracted, 4 is subtracted from 5. Since 4 is the nearest value of 5, now 4 is subtracted. So place a 1 in below 4. Here we do not use 8. So there is a 0 here. Since at first 2 to the power 4, 2 to the power 3, 2 to the power 2. But 2 to the power 3, that means 8, is does not used here for subtractions. So place 0 here. Next 1, we have to reach 0. So 1 is subtracted from 1 and it becomes 0. Now the value of 1 is 2 to the power 0. So place a 1 here. Now in this to reach from 1 to 0, we does not here use 2. That is, this positions we does not use. So 2, place a 0 below the 2. So which digit is not subtracted, that means which digit, that is power of 2, is not subtracted from the number, then it places 0, and if it is subtracted, then it is placed 1. In this way we get 1, 0, 1, 0, 1. This is a binary number. Another example is 56. Now 56 nearest lowest value is 32. 32 is subtracted from 56. So place a 1. Now after subtracting we get 24. 24's nearest value is 16. So 16 again subtracted and place a 1. And 16's nearest value in the multiple of 2 is 8. Then 8 is subtracted from 8 and it becomes 0. Now there is no number remains, the number becomes 0. So all the values are 0, remaining values. Since 4 to 1 positions is not entered here for subtractions. So only 32, 16 and 8. These 3 positions is entered here for subtractions. So their values is 1, 1, 1. And remaining 3 values is 0, 0, 0. The binary numbers value is, binary number of 56 is 1, 1, 0, 0, 0. Here in this class we study the about the what is the objectives and syllabus. We see the syllabus of the computer architectures and read the how binary number is decimal is binary, decimal number is converted to binary, and how binary number is converted into decimal. We used here 2 different methods. First is division method, second is subtraction method. In next class we will say the subsequent number conversions. Thank you.